Hello, am I audible?
Yes, sir.
Is the screen visible?
Yes, sir.
In the last lecture, we had seen up to this part. Correct? I hope you recollect. So we discussed in the morning also in the lab session our inlet condition to the compressor, low pressure or low temperature, basically atmospheric pressure, atmospheric temperature. Let's say. Then after the compression, high pressure, high temperature. In the condenser, it is a high pressure, but not the vapor phase. It would be naturally a superheated part. So superheated to saturated vapor, then phase change, saturated vapor to saturated liquid, and maybe even if further required, saturated liquid to subcooled liquid. So that solely depends on our design. So that is the condenser part. Then in the throttling, because of the expansion, pressure reduces, temperature further reduces, that is the lowest one. And once it gets exposed to the evaporator, then it will extract the heat and comes back to the original condition, that is state 1. Okay. This is how our cycle gets complete. What are the merits? Basically, high COP. This is because we resemble this particular cycle very close to the Carnot cycle, Carnot refrigerator. So isentropic compression remains as it is. Isothermal heat rejection, that is condenser. Isothermal heat absorption, that is evaporator. The only process that is getting deviated is the isentropic expansion. We do not use any turbine over here as the isentropic expansion. We use that simple capillary or thermostatic expansion valve or something like that, throttle valve. And throttling is a irreversible process, we know. Okay, so out of 4, 3 processes are as the same as those of the Carnot cycle, Carnot refrigerator. So that is why the COP is very close to that of the Carnot COP. Do you agree? Isenthalpic expansion is the only irreversible part. 2 isothermal and 1 isentropic is same.
Yes.
Second, running cost is around 1/5 of that of the refrigeration cost. Why? Because your equipment are very small now. For the air refrigeration, we have seen that air mass is very abundantly required, large. Here, the refrigerant, we are making use of the phase change. In the air refrigeration, everything is sensible heat, absorption or rejection. But in vapor compression cycle, the refrigerant which we are using is continuously changing the phase. So like even very small amount of 5 ml, 10 ml liquid is sufficient. Correct? So the size drastically reduces. Size of the evaporator small. That is the same part because we are basically focusing towards the latent heat, not the sensible heat. And the fourth part, evaporator temperature adjustment, is very simple. The throttle valve you just change. Now you recollect, maybe in your childhood days, you must have observed what your father or mother at the home would be changing some valve setting inside the evaporator section of the domestic refrigerator. कोई तो एक valve वो हिलाते थे, घुमाते थे. If you have observed carefully. Had you observed any time or not? Yes or no? No one had observed. Shame on you.
No, sir, you haven't observed.
Why so? आपके बचपन के जमाने में ऑटोमेटिक फ्रिज नहीं थी. आई नो इट.
तो एकदम बॅक साइड को होता था सर, थोडा घुमाने का टाइप.
काय?
हो बोलताय काय ते पार्टच्या साइडला असं ते बोलताय का तुम्ही?
नाही, evaporator section inside that chamber when you open the door generally on left or right side, not at the back. Left or right side there is a very small knob. आता येत नाहीत. Nowadays it is gone. That's why I told, maybe in your childhood days you might have observed. And your father or mother used to change the setting. Generally in terms of temperatures, it is given like 5 degree, 10 degree, 0 degree, -5 degree. That is the evaporator setting, temperature setting. Very easy to change it. If there is a small amount of load, lesser amount, then why to unnecessarily chill it? If it is a large amount, you have to make the temperature on the lower side so that refrigeration effect would be better. काय कटकट आहे रांडेची, कोण आहे? इकडे इकडे तुम्ही नाही ओंकार. हा अगं आवाज येतोय ना? ते बाहेर जाऊन त्यांना सांगायचं सरांचं लेक्चर संपेपर्यंत आता आवाज आला ना हात धरून बाहेर काढीन एकेकाला. मूर्ख कुठले, नको त्या वेळेला नको ती कामं करायची अंगात आल्यासारखी. Okay. Now the demerits. Now our initial cost is high because we have to design a compressor which can handle two phases, correct? Even the expansion device also. There is a
Yes.
vapor phase, there is a liquid phase. So naturally the compressor design changes. We have to take into consideration all those factors as the dryness fraction, liquid zone, naturally higher. The air compressor to design is very simple. Vapor compressor naturally difficult. Correct. Second part, inflammability. Your refrigerant is prone for any what we can say explosion. Correct. So inflammability issue is always there. We have to be very careful while compressing the refrigerant, because unnecessarily high compression ratio will give me unnecessarily high temperature, and then even a small spark or anything, and the entire system will put on fire. So that is a very serious issue. And the third part is leakage. It's a refrigerant. If it gets leaked out, so that means your M dot reduces, your refrigeration effect reduces. एयर के लिए कोई फर्क नहीं पड़ता है, इट इज ओपन टू एटमॉस्फेयर, बाहर जाएगी अंदर आएगी. But for the refrigerant, it's very, very important. Unnecessarily, you have to fill it again and again. Correct? So that is the most important demerit. One is the cost, second is the fire hazards, third is the leakage. Leakage and even toxicity, because all the CFCs are chlorofluorocarbons, refrigerants, so naturally toxicity. They are very toxic. We cannot put them like open to the atmosphere if there is any kind of leakage. So safety issue, safety hazards is the important factor as far as the limitations are concerned. Okay, air ke liye there is no toxicity, no issues. Clear? Now we come. Any doubt in this?
No, sir.
No, sir.
Okay. Now we come for those different cases, what we are actually going to deal with in our practical. First practical. So dry and saturated vapor after compression. So I am drawing over here the TS chart only because you are quite familiar with that. I have not yet shifted to pH. But that I will do afterwards. Let us try to analyze the performance first. So this is my dry and saturated vapor after compression. So that means at 0.2, correct?
Yes, sir.
Right. Then the condensation, we assume that the condensation means the condenser stops over here. Then this is the throttling process and then the evaporator. So what is my refrigeration load is this 4 to 1. My compressor work is this 1 to 2. However, this work deals with the gas plus vapor, liquid plus vapor. No, gas plus vapor, no, liquid plus vapor. So naturally this work will be much higher. Compressing the gas is easier than compressing the liquid. The liquid itself is incompressible when we see. So if still you want to compress it, that means the work is higher. COP is lower. and even refrigeration effect is also lower. Correct? So over here I will say H1 minus H4 and H2 minus H1. This is my compressor work. Correct? On the TS chart, inside the loop cycle is the work. Basically heat and then work finally. And this is my net refrigeration effect. Correct? So this H1 minus H4 is my refrigeration load. H2 minus H1 is my compressor work. Fine with this figure.
Yes, sir.
Now I change this part, dry and saturated after the compression. Now I will say superheated vapor after compression. Instead of limiting over here, I shift it on this side. This is what is our case in practical, correct? We are starting from here. Dry and saturated at the start of the compression. Second case is dry and saturated at the end of the compression. We call it as a wet compression.
Yes,
So
sir.
similar case over here. So let's say somewhere over here, my starting point. So naturally my compression process ends up at the superheat. Okay. Because your pressure lines are something like this. I hope you remember TS diagram. Inside the dome it is horizontal, but outside the dome it is having the slope, constant
Yes.
pressure lines.
Yes,
Correct?
sir.
Rankine cycle.
Yes, sir.
Rankine cycle ulta hai. That is engine. This is the refrigerator. So here I start the compression process from this one, end up at 2, which is at the superheated part. So again, the logically your heat absorbed is as the same as 1 to 4. But now you can see that instead of like this, point 1 now is shifted on the right hand side. So that means it is increased in the refrigeration effect. Do you agree?
Yes, sir.
Whereas in the denominator work done earlier, it was like this. But now it is this higher increase. So your denominator also increased. In short, what I'm trying to say is numerator is also increased, denominator also increased. I cannot predict about what happens to the COP. It may remain same, it may increase, it may decrease also. It solely depends on the values. Do you agree?
Yes, sir.
So the first case which we discussed is this. Here the problem is that wet compression. The compressor has to deal with the wet part, liquid plus vapor. You shift it from this particular point to this particular point because I want to get rid of that liquid part. Fine, your refrigeration effect is increased, but your compressor work also increases. So again, no control on the COP. I cannot say that it is increased 100%. It depends on the values. This figure basically ultimately, so in compression process, anything after the saturation is superheated. So my refrigeration effect is increased, my compressor work is also increased. I may get the same ratio. Numerator be increased, denominator be increased. I can have the same ratio. It solely depends on the values. So this method also doesn't ensure that my COP would be better. Correct? Third part, total wet compression. So here you observe that evaporation effect is reduced, refrigeration effect. And this is still further on the left side, not even reaching to the saturated part. This is also liquid plus vapor. This is also liquid plus vapor. Compressor work is also on a much larger scale because liquid plus vapor and evaporation effect is reduced. Earlier it was at least up to this part. Correct? Saturation. Now to even reduced. So again, formula is same. H1 minus H4, H2 minus H1. But here H2 itself is the liquid part. Liquid in the sense two phase. So this is less than what I can say H2 saturated. H2 saturated is somewhat more over here. this location, this state. This is even having the dryness fraction, so even lower. So this method also doesn't ensure that COP would be better. Do you agree?
Yes, sir.
Yes,
So
sir.
there is always one problem, or either of the problems. One, I need to deal with the liquid plus vapor part, and if I want to get rid of that, that means the evaporation process gets executed up to the saturated part. It's complicated. Complicated in the sense higher enthalpy. So we have to somehow manage the balance between these. How much would be the percentage increase in the evaporation load, and how much would be the percentage increase in the compressor work required? If I can manage it, I can enhance the COP. Agree?
Yes, sir.
Now I will introduce the pH diagram. अभी तक हमने TS देखा था, correct? So on the pressure enthalpy diagram, why do I need enthalpy? Because in the morning session only we discussed everything is related to enthalpy, correct? H1, H2, H4, all enthalpy terms. So instead of TS, from which tracing the enthalpy part is very difficult, on PV so it is almost impossible. So we convert as the enthalpy chart itself. And what I need to know is the basic part is the pressure, condenser pressure and evaporator pressure. So that is why we suitably convert this entire interpretation, graphical interpretation, as the pH1, so that I can directly draw a horizontal line like a condenser pressure. I can directly draw another horizontal line as a evaporator pressure. Why pressure would change? Whatever it is phase, pressure remains same, correct?
Yes,
Why
sir.
it would change? So liquid pressure or vapor pressure, it is one and the same. It's only that the enthalpy would change. So that is why on the y-axis there is pressure. On the x-axis directly I will take the projection so that I will directly read the enthalpy value. So this chart also remains more or less similar. Saturated liquid line, okay, saturated vapor line. Here only difference is that the slope of this on the TS chart it is generally moving towards the right hand side. Here the slope again comes back towards the left again. That is the only difference. Because your latent part is restricted, limited. Okay. So here there is a critical point. Left hand side is saturated liquid, right hand side is saturated vapor. Okay. This is my subcooled region, same as steam. Then superheated, then two phase. I hope you recollect this two phase and all.
Yes, sir.
Same three thermodynamics. Okay. Then horizontal line, constant pressure, isobaric. The vertical line, that is isenthalpic. Correct? Enthalpy constant. Then a temperature line. You will always observe it will be like a vertical one. Okay. Why? Because the liquid is an incompressible one. So why enthalpy would change? Even though let's say you are tracing this way. So even though the pressure reduces, it is a liquid part. Volume remains almost same. Very, very nominal change. So then naturally, if there is no PDV part, then why enthalpy would change? It also remains almost same. Correct. Then this is latent part. Pressure is constant. Temperature is also constant. Correct. And then further over here, the slope drastically changes because now you are in a superheated region. Agree?
Yes, sir.
Here
Yes,
it
sir.
is acting more like a gas. Here it is like a liquid. Fine. The slope of the isochoric part, isochoric process, V is equal to constant, is lower than that of the isentropic compression process particularly. slope of the isentropic process is larger, isochoric process is lower. Fine. So our part, our cycle analysis, per compression cycle analysis, deals with isentropic compression, okay, isothermal heat rejection, or rather I should say isobaric heat rejection, because condenser pressure remains same, even though it may be somewhere here, let's say, superheated. Pressure would not change. It's a heat exchanger, it is rejecting the heat. Why pressure would change? Correct. So I will say isobaric heat rejection, then isenthalpic expansion, and then again isobaric heat addition. Do you agree? So there will be two horizontal lines, one inclined line, isentropic compression, and one vertical line. That is isentropic expansion. There is no such case. ऊपर गया फिर से नीचे आया, no tilted part. On the TS chart, temperature increases over here. We have to put it as a tilted one. But pressure doesn't change. This is a constant pressure line, correct? This one. Here, here, here. This is a constant pressure line. So temperature may change, but pressure would not change. That is the biggest advantage. So here, temperature would be different. The temperature over here different than here, then here, then here, then here, like that. But pressure is same. Do you agree?
Yes, sir.
Yes.
So that is why we now get a simplified version on the graphical interpretation, including two horizontal lines, one inclined line for the compression and one vertical line for the expansion, as the simplest possible as it could be. Do you agree?
Yes, sir.
So this is the biggest advantage of the pH chart. I need not worry ये superheat हुआ नहीं हुआ, still the pressure is same, constant. And this is the dryness fraction lines, so x equal to 0.1, 0.2, 0.3, and likewise. Now we will try to shift our TS chart, matlab ye, whatever we had just seen, these three cases, into the pH version. This is my, let's say, isentropic compression, starting from the saturated vapor, then superheated vapor. I can see this, that okay, it is outside on the right hand side of the saturated vapor. So that means this is superheated, simple. These are the temperature lines you can see. Then horizontal, and then moving like this. So naturally this temperature line and this temperature line are different. Now you open that ASHRAE chart, ASHRAE booklet which I shared in the morning, and you will find the similar type of chart for every refrigerant. Okay, this is for 404A. You can find it for R11, R12, R22, R134A, 717, 714, anything. Carbon dioxide, ammonia, 744, anything. Fine. So
Yes,
this
sir.
is how the chart
Yes.
looks. Now what I will do, this is my state 1. So directly H1. This is my state 2, isentropic compression. So this is my H2. हो गया काम, I need not use any calculator. I need not use any equation to find out the enthalpy values. And H3 is equal to H4. Isenthalpy, I know. And now here you will get the answer for the question which I had asked in the morning. Like this, if you draw, then this is the subcooled part. ये saturated liquid है. इसके left hand side means liquid. So this is subcooled. correct? And then you start for the liquid expansion. So initially it will expand, reach to the saturation part. And then it will enter into the two-phase zone. So design of this process is very, very, very difficult. Liquid expansion. Gas expansion is simple. And this is the reason we do not use the turbine. How you will expand the liquid in the turbine? Compressor part is simple. It is gas. But expansion part is very difficult. It is liquid plus vapor. Initially, start to itself is liquid. At the end, liquid plus vapor. So this is always a theoretical assumption that the process is an isenthalpic expansion. The closer you try to attach to this theoretical assumption that the enthalpy remaining constant, better is your performance. There is absolutely no practical guarantee that the enthalpy would be constant. So we design the process, not process, process, 3 to 4. Design the process or design the expansion valve in such a way that I can stick as close as possible to the isenthalpic assumption. In reality, in practice, isenthalpic expansion never takes place. It is very easy to assume for the gaseous part, but not for the liquid part. Do you agree?
Yes, sir.
Very good. So my refrigeration effect is H1 minus H4. You can read directly the values. This is H1, this is H4. What is the compressor work? H2 minus H1. बस 4 projections नीचे लेना है, खत्म. 4 means 3 ही, because 3 and 4 is same. Correct? So 3 projection नीचे ले लिया, enthalpy values मिल गए, substitute in the formula, calculate the answer. Job is done. This is almost impossible in PV and very, very difficult in TS. This is why we convert everything into pH. And now you will appreciate that so many people have done so many things for you readily available. Correct? All these charts are readily available. I have to just use it, calculate the value, put it in formula, find out the performance. Hundreds of people have put their efforts to generate such graph. Correct? Now, factors affecting the vapor compression cycle. This is our experiment number 2. Experiment number 1 is that water cooler. Experiment number 2 is the parametric evaluation. That means factors. So there we will be analyzing the effect of condenser pressure and effect of evaporator pressure. Okay. So up to this point, any doubt to anyone? Basic concept. उसके बाद ही मैं उसके factors पे जाऊंगा. Effect of factor has to be discussed only after the basic thing is clear. Any doubt to anyone in the entire class?
No, sir.
Okay, fine, good. So factors, let us see. Effect of suction pressure. Suction means compressor suction. That means evaporator. Do you agree?
Yes,
Yes.
sir.
So here I reduce the pressure. What is the effect? Saturation point iska slope. The slope of the saturated vapor is towards the left hand side only, not towards the right hand side like this. On the TS chart, it is always on the right hand side. So advantages. Here it is disadvantages. It is towards the left hand side only. So saturation comes over here. तो इसके कम है. This is isenthalpic one. You cannot change. So my refrigeration effect is reduced. Do you agree?
Yes, sir.
And to reach to the same condenser pressure, naturally compressor work is increased. Correct?
Yes,
Yes,
sir.
sir. COP
So my refrigeration effect is reduced, work input is increased, COP is bound to reduce. Correct? So unnecessarily reducing the evaporator pressure will be ultimately resulting in a reduction in COP. And basically we know that this is more related towards the work. So you are increasing the area, that means work is increased. Even the refrigeration effect may remain same, but the work is increased. The COP is bound to reduce. Correct? Any doubt?
No, sir.
Now the second part, effect of the delivery pressure. So here I have shown delivery pressure increased. Now at this higher pressure, the saturation liquid point naturally shifts toward the right hand side of this. Earlier it was 3, now it is 3 dash right hand side, because the slope of this is like this, left hand side of. And then this 3 dash to 4 dash is my isenthalpic expansion. So now my refrigeration effect is reduced 1 to 4 initial. Now it is 1 to 4 dash only. Do you agree? And compressor work is
Yes, sir.
increased.
COP will decrease.
So same refrigeration effect reduce, work input increased, compressor work COP reduced. Further part, question arises, why to stop here? Okay, fine. You go up to this part, subcooled. Still, what you can do is to maintain the refrigeration effect constant, but still work input is increased. Do you agree?
Yes,
Yes,
sir.
sir.
So whatever you do, your COP is bound to reduce. Correct? Now the third part, effect of the superheating. Instead of starting the compression process itself as a saturated one, if I take it as a superheated one, then what happens? The slope of the isentropic curve continuously changes. So the slope over here is larger than slope of this. It would be larger than slope of this. It would be larger than slope of this. It basically gets flattened. As you go on towards the right hand side in the superheated part, the isentropic curve goes on flattening. Let us try to see if possible here. May not be possible here. No, not possible here. Let's wait. Where is your chart? Ashray. No. Open the Ashray chart. याची अजून एक काढून ठेवा, मग आपल्यालाच लागेल ना नंतर परत. तुम्ही पण देताय काय?
आणि ते चालू करतो.
नाही, हे तुम्ही हे देताय का? क्वेरी म्हणजे हा रिक्विजिशन साठी देताय का एक्सटेन्शन साठी देताय?
आधी रिक्विजिशन नंतर एक्सटेन्शन. आधी अप्रूव्ह तर होऊ दे ना.
अप्रूव्ह काय व्हायचं त्याच्यात? हेच अप्रूव्हल आहे.
आम्ही म्हणतोय की एकच माणूस जर डिस्ट्रीब्युटर त्याला द्या.
अच्छा, म्हणजे ते हो, ते ओरिजिनल द्यायचं असतं स्टोअर्सला.
नाही ती नंतर.
आम्ही आता स्टोअर मध्ये दिलं, तुम्ही स्टोअरला नाही देणार ना. हा, मग त्याला जाऊ दे डायरेक्ट. नुसतं तरी एकदा त्यांची घेऊन टाका ना. ओके, कमिंग बॅक टू अवर वर्क. This I think is better. Let me share this. This is your Can you see the screen?
Yes, sir.
Yes, sir.
So this is my x-axis enthalpy. Okay, इसको 90 degree tilt करना है, and you will see this S, that is entropy, 2 kJ per kg Kelvin. So now you observe this slope and let's say this slope. They are different. So it's basically tends to get flattened. As you go on towards the right hand side, it gets flattened. इसको 90 degree उल्टा tilt करो, assume, and then see that this slope, okay, and this slope, they are slightly different. Slightly नहीं, अच्छा खासा different. So as you go on towards the superheated part, that means this is saturated, this is superheated, further superheated, further superheated. Then this slope is larger than this slope, which is flattened. Do you agree? Let me
Yes, sir.
wait. Let me find out that old version. Where is that file? Shri. Yes. This is the old version, 1997 actually. I had shared with you the latest one. This one is the old one. Let me share this. This will give you a better idea. Can you see this?
Yes, sir.
This is R11. Okay. And these are the isentropic curves. Can you see? S is equal to 1.8 लिखा हुआ है. So now you observe 1.70 ka slope, tilt, and 2.1 the last. They are different. It is like getting somewhat flattened towards the right hand side. Are you clear now?
Yes, sir.
So this is the reason if you start, this is my saturation liquid, and here this is saturation vapor. Here लिखा हुआ है देखो, saturated vapor. Okay. So the moment you start going out of this, that means towards the more and more superheated part, then the slope of this compression, isentropic compression, that is getting flattened. And flat slope, that means more work. Do you agree? Now let us go back to this slide. If I come on the right hand side, then this becomes flat, and the pressure limit here and here is fixed, that you cannot change. So that means your H2 dash or H2 double dash or H2 triple dash, whatever it is, would be much larger. Do you agree?
Yes, sir.
Correct. So H2 dash and H1 dash will be larger than H2 and H1. Means minus sign, I should say. H2 dash minus H1 dash is larger than H2 minus H1. Let's assume third point over here. The slope is again flattened. So let's say I go like this, somewhere here. So H2 double dash minus H1 double dash would be much larger. Do you agree? This would be somewhere here, let's say. I'm exaggerating, but the point to be highlighted is this, that the slopes are different. They are not like parallel lines to each other. So H2 double dash minus H1 double dash will be much larger. When you take the projection on the x-axis, enthalpy, H2 double dash somewhere here, H1 double dash somewhere here, would be much larger than this. So ultimately, what changes is the compressor work. So even though increase in the refrigeration effect, there is increase in the compressor work also. Correct? So refrigeration effect is increase. Instead of 1 to 4, or rather 4 to 1, it is now 4 to 1 dash increase. But subsequently, This also increases. H2 dash minus H1 dash. So this compressor work may increase or decrease or may remain same. That solely depends on the values of the pressure. Correct. So accordingly, COP may increase also, COP may remain constant also, COP may even reduce also. This is not a assured method. Do you agree?
Yes, sir.
Correct. Larger the pressure difference between the evaporator and the condenser, naturally larger would be the delta H. Smaller the difference, smaller. So here again it goes as the percentage. Percentage increase in the refrigeration effect and percentage increase in the compressor work. Solely depends on that. So COP may be reduced, COP may be increased also, COP may even remain constant also. Whatever is the change in this refrigeration effect 1 to 1 dash and whatever is the change in the compressor work means H2 minus H1 and H2 dash minus H1 dash. If that is also same, then COP also will be same. So it may remain constant also. It may reduce also, it may increase also. So it really depends on the operating conditions. Are you getting this clear? Yes or no? Any doubt?
No, sir, no doubt.
Okay, so this gives me another clear hint that unnecessarily superheating the gas does not ensure that my performance would be better. हाँ, वो कब होता जब ये दोनों लाइंस स्लोप्स सेम, दोनों लाइंस पैरेलल होते, तो then there is no difference. इसको शिफ्ट किया, this continuous line if gets shifted by some distance over here, then the difference would be same. Here the difference is increased, so I would have said okay, COP is increased, but that is not the case. The difference between 1 dash and 2 dash are not same. They are not parallel lines. Fine. So this is also a method which cannot assure 100% that superheating will increase the COP. It may not. Anything can happen. So the fourth method, that is the effect of subcooling. You go on subcooled, achieving the subcooled liquid. Do not stop at the heat rejection at 0.3. Let it go to 3 dash. That is always possible. Now you are rejecting the heat. Reject more amount of heat. Here it is a superheated vapor. It comes over here. Let's say 2 dash. Saturated vapor. Further heat rejection, phase change 3. Now go to this 3 dash subcooled. Constant pressure, heat rejection. This is always possible. But because of this, what happens is 3 dash to 4 dash is my isenthalpic expansion process. Now compressor work is same. उसमें थोड़ी कोई change है, but my refrigeration effect is increased. Instead of 1.4, now this is 1 minus 4 dash. The compressor work is same, but refrigeration effect is increased, and as such COP increases. So this is the only assured method for the increase in COP. Do you agree?
Yes, sir.
What we are doing is towards the expansion side, compression side remaining same. In all the 3 earlier methods, we were changing the compression side. Suction pressure, compressor side change. Delivery pressure, compressor side change. Superheating, compression side change. So naturally there is a problem. I will keep the compressor same so that input is same and output increased. So for that, instead of right hand side compressor, I will try to do something on the left hand side, that is the expansion. That will be assured technique for the increase in COP. Do you agree?
Yes, sir, agree.
Fine. Suction and condenser temperature. That is evaporator and condenser temperature. So here we'll know the basic law. Low temperature should be as high as possible and high temperature should be as low as possible. That is what we had seen at the basic part, chapter 1 itself. Correct? So reduce the condenser temperature. Why? High temperature should be as low as possible and increase the evaporator temperature. Low temperature should be as high as possible. I hope you recollect this chapter 1.
Yes, sir.
Correct? So basically what you are squeezing is the area inside the dome, which is related to the work. So work is reduced. Then this increases. Yeah. Earlier, let's say evaporation effect is 1 to 4. Now the 1 is same over here, vertical line, but 4 dash that is shifted towards the left hand side. So overall refrigeration effect increases. Correct? So finally my COP increases. Refrigeration effect increase, compressor work reduce, so COP has to increase. So now the exercise for you people today is to check for the suction condenser pressure or temperature, whatever. Open the manual of whatever company and make of the or model of the domestic refrigerator you have. Check the refrigerant, whether it is 134A or 404 or 410, whatever it is. Okay, and check the pressures and corresponding temperatures for the condenser and the evaporator, and try to plot on the pH chart. The entire bunch of, like, all the refrigerant pH charts are given to you in the lab session, S3 handbook. So cross check it. Very simple job and very interesting also. Do you agree? We understood the effect.
Yes, sir.
Okay. Now instead of this, how much time left?
5-10 minutes.
So let me now link this with our lab, because that is something which we are going to do immediately next session of the lab, correct? Friday. So what we have done over there is m dot into Cp into delta T, that is the water part, assuming that 100% heat transfer taking place because of the first law of thermodynamics, correct? So that will give me the refrigeration effect. In the denominator, it is the compressor work, which you have calculated with the help of that energy meter, correct? Constant and all such kind of things.
Yes.
And what you got is the COP experimental. Now you try to shift that entire cycle. The batches we have already made, correct? 25, then 26 to 50 and 51 onwards. So try to shift that cycle on the pH chart. It is R12, correct? So R12 pH chart is with you. Try to draw the lines related to the condenser pressure and evaporator pressure. Fine, that is a simple task. You have calculated it in megapascal. So, and it is the graph is also in megapascal. So try to do that interpolation and try to plot it. Or rather, you don't do it, I will tell you, because we have not yet solved any numerical as such. So we will do that in some next session. By the way, when is our next lecture? Tomorrow, shifted, correct? Transferred lecture.
Yes, sir. Tomorrow.
So tomorrow we will do this lab part in our theory lecture. Fine.
Yes, sir.
So that it will be a good practice for you. Now I will just summarize about this mathematical analysis. What is refrigeration effect? H1 minus H4. May it include the latent part and the superheated part, whatever it is. Correct? Then mass of the refrigerant, how you will calculate it. So now we know about 1 ton. What is 1 ton? 12,660 corresponding. Correct? Kilojoule per hour. And this is your specific enthalpy difference. So that is kilojoule per kg. Correct? So you can substitute in this formula. This is the total total 1 ton refrigeration effect. This is a specific refrigeration effect. 3600 is just for the sake of converting to per hour to per second. And you will calculate the mass. So basically mass flow rate. This is kg per second per ton. If your capacity is 5 tons, multiply by 5 to this. As same as that. Correct?
Yes.
Theoretical piston displacement. What piston displacement is? Mass into the specific volume. That is the total displacement. So specific volume of the refrigerant you can read from the chart, pH chart. Either there would be specific volume lines given or the density lines given because they are reciprocal. Density is kg per meter cube. Specific volume is meter cube per kg. So either there would be specific volume lines given or the density lines given. I can find out from density line about the specific volume. So specific volume at the inlet condition. Correct. Let's say density at the inlet condition given, take its reciprocal, that is specific volume, multiply by the mass, which you can calculate from here. So that will give me the total displacement of the piston. Correct. So this is my mass just now calculated over here, multiplied by Vg at the inlet, because compressor
sir.
inlet. Right. Then power developed. Same m dot into delta H. Delta H is kg per kg. This is kg per second. So it will be kg per second or kilowatt. If it is a polytropic compression, I have to go with this P2 V2 minus P1 V1. Whatever is that. So that becomes like a difficult task for us. N upon n minus 1. Fine, it's a gaseous part, not a problem, as such a big problem, but a difficult one. What we assume is the adiabatic compression, isentropic one. If it is not and the polytropic one, then I have to know about the n value. And then this P2, V2, and P1, V1. Out of which P2, P1 is okay, V1, V2 is difficult. For that, you need to know about the compressor dimensions. Correct? Heat removed through the condenser. Condenser means heat rejection. That is process 2 to 3. So m dot into H2 minus H3. H2 is higher. Correct? Okay, we'll solve this numerical in the next lecture. Fine. Any doubt?
No, sir.
after
Thank you,
this?
sir.
Fine. So we'll end up over here. I think in the next lecture, tomorrow's lecture, I will start with the numerical over here first. That means theory lecture. And once we start with the pH chart, there are certain numericals solved by making use of the basic thermodynamic laws and certain by making use of the pH chart. You must be able to solve by any method, whatever I may ask in the exam. If I ask you to solve by theory, then you have to use all the thermodynamic equations. If I ask you to use the pH chart, then you have to use the pH chart. So I have taken the what do you call, both ways. Couple of numericals by thermodynamic formulae, couple of numericals by using the pH chart. Variety. Okay. So once I come to the pH chart,